Everybody's getting let into the waiting room. So we'll wait just 2-3 minutes, give people a chance to arrive and get brought into our Zoom meeting from the waiting room. We're looking good. Good evening. Good. Okay, like I said, I'm just going to fill a little space here for another 3 minutes or so people have a chance to come and get let in to the meeting. So you are at the correct place. This is Friends of Fission Northwest. Good evening. And we're waiting just another, say, 2 minutes, and we'll get started. I see several people's names that we know. Welcome, and welcome to everybody. Okay, so where are we? Let's get started. So Friends of Fission Northwest wants to welcome all of you to tonight, and I'm Paula King. And before I introduce our speaker, I'm going to mention just a couple of upcoming events. On March the 2nd, we're going to have a panel discussion with members of the Board of Generation Atomic. And that's a free get-together at Bickerson's Brewhouse in Ballard. It's a great space and lots of good beer. If you're beer drinkers, they have soft drinks. I don't know yet if we're going to have a food truck. We'll let you know in our publicity. It's going to be a lively group who've been organizing here in Europe to promote nuclear power, helping other organizations like in Europe get together to promote nuclear power. They've done street theater. They've helped organize a march that went from San Francisco to Sacramento in California to help save Diablo Canyon nuclear plant. And that was the last nuclear power plant left in California, and it is now being kept open for now anyway. So watch for that event. On March 21st, Nick Turin, who's one of our great speakers, he works for TerraPower. He is works on designs for advanced nuclear power reactors, and he's giving a talk to the meetup group, Seattle Skeptics and Science Enthusiasts, in the downstairs of Razi's Pizzeria about nuclear power. I'm not quite sure what all his details are. We're going to learn when we put out the publicity. So everybody's welcome to go. And if you aren't on our mailing list or part of our meetup group, then you can send me your email by chat, and I'll put you on. We send emails to announce events. I don't have time to send tons of emails out, so don't worry, you're not going to get bombarded. So tonight we have Tom Ackerman. He's a professor emeritus of atmospheric sciences at the University of Washington. He was professor of atmospheric sciences and director of the Joint Institute for the Study of Atmosphere and Ocean at the UW from 2007 to 2018. And Tom is the recipient of the NASA Distinguished Public Service Medal and the Leo Szilard Award for Science in the Public Interest, awarded by the American Physical Society. He's a fellow of both the American Association for the Advancement of Science and the American Geophysical Union. And he's done lots more than that. We gave you the short version there. So he's going to talk to us tonight about messing with Mother Nature, climate change, and climate engineering. So enjoy.
Yeah, somebody is bombing the screen. Okay, well. Well, let's just go ahead and see what happens. Can you all hear me fine? Just nod knowingly.
Yes, we can hear you.
Okay. You don't have to blank out all your little windows. A few people looking at me in windows would be good. Thank you. I like to know that I'm talking to somebody. This whole Zoom experience can be a little disconcerting. Thank you for inviting me, Paula. I'm happy to be here. For those of you who don't know, the title emeritus means that basically they don't pay you anymore at the university, but they still want work from you. I still am doing research. I still have a graduate student that I'm advising, and I will actually be teaching a course most probably next year. So I'm not completely free. So this is a complex problem we're going to talk about. And the problem of dealing with a complex problem in a short amount of time is it's a little bit like stone skipping. You hop from topic to topic to topic without having a chance. No, here we go again with the bombing. Okay. So if there are things that I don't answer, feel free to write down a question and we'll talk about them at the end. If we were doing this in person, which would be much nicer, I would tell you to interrupt me as I go, but it's really hard on Zoom, I find, to keep track of the interruptions. So we're going to do a quick overview of Earth energetics. We're going to talk about what is climate engineering, and then we're going to talk a little bit about ethics and governance associated with climate engineering. So this is, as we all know, Mother Nature. The energetics of a planet are pretty straightforward. Solar radiation comes into the planet and heats it up, and infrared radiation is emitted from the planet and cools it down. If you orbit a spacecraft outside the Earth's atmosphere and you measure the effective temperature of the planet from space, you would get a temperature around 255 Kelvin or minus 17 degrees centigrade, which for those of you who don't do centigrade is still pretty cold. And obviously the surface is not at that temperature. So the question is always, why does it appear to be so cold from the outside? Well, there's this side of the infrared radiation problem, which is not only emitting infrared radiation and cooling the planet down to space, but the atmosphere around the planet is radiating that infrared radiation back down to the Earth and warming it up. The scale here is actually really misleading. If you pick up a big old, remember those big old hard globes we had hanging around in the classroom? The thickness of the atmosphere relative to that globe is kind of like the layer of varnish that's on the globe. That's all that we're talking about when we talk about all of this atmospheric greenhouse effect, is that very thin piece. Increasing greenhouse gas concentrations increases the atmospheric warming potential, increases the downward infrared radiation, and therefore warms the surface. Oh, here we go again. In the problem of the Earth radiation balance, this actually has numbers on them, and this is a percentage of the incoming radiation. Incoming radiation up here is 100%, and about half of that radiation gets to the surface, but 100% equivalent comes from infrared radiation. In other words, the Earth's surface is warmed more by infrared radiation from the atmosphere than it is by the sun. And you're going to say, oh, that's not possible. Well, it is, because the infrared radiation works day and night, and solar radiation only works in the daytime and not that often in Seattle in the winter. So it's important to remember that this greenhouse effect is what maintains the climate that we have. Oh, lovely. What happens to all this surface radiation energy that gets absorbed at the surface? Well, some of it is transferred back to the atmosphere. This is the net difference between down and up. But most of it goes into this term right here, which is evaporation. So most of the energy that is absorbed at the surface actually is used not to heat anything, but to evaporate water. Are you all seeing these flying people?
Yeah, thank you.
All right. The global hydrologic cycle is also an important part of the climate energetics. Basically, you can think about the atmosphere here as kind of a bucket, and there's evaporation putting water in it, and there are precipitation that's allowing the water to run out of the bucket. When you have an equilibrium between what's coming in and what's going out, which is the typical state of the atmosphere, there's no change in the amount in the bucket. In other words, the amount of water in the atmosphere stays about the same. When we warm the air, we can put more water into the air. And the ocean essentially supplies an infinite amount of water as far as the atmosphere is concerned. A warmer atmosphere has the total higher water content, but that also ends up increasing, as we'll see in a minute, the absorption and re-emission of infrared radiation. Okay, so that's your basic crash course. What's important? Downward infrared radiation, which is governed by greenhouse gases, water vapor, which goes up in response to temperature going up. All right. So messing with Mother Nature, we all know that we've been messing with Mother Nature. Transportation, power, manufacturing. So how do greenhouse gases work? Principal greenhouse gases in our atmosphere are water vapor and carbon dioxide. There's a contribution from a bunch of other gases, ozone, methane, nitrogen oxide, freons. Human activity contributes to all of these. So we're increasing greenhouse gases, not just in carbon dioxide. The reason we focus a lot on carbon dioxide is because carbon dioxide is very long lasting. Once in the atmosphere, can stay for hundreds to thousands of years. The concentration of water vapor is always limited by atmospheric temperature. And even though water vapor is the most important greenhouse gas, it is not the regulatory gas because it's controlled by the temperature. I hope that makes sense. Okay, so what's going on with carbon dioxide concentration? This is a map of the concentration of carbon dioxide measured at Mauna Loa Observatory. This may be the most iconic measurement in all of climate science. It was started in 1957, something called the International Geophysical Year. David Keeling, who was at that time a professor at Scripps Institute of Oceanography, lobbied the federal government to give him some money to start making CO2 measurements at Mauna Loa. And I'm recounting this because people didn't want to give him the money. They said there's nothing fancy about measuring CO2, so why bother? Well, this is Mauna Loa Observatory. He started doing these measurements, so I should go back. Whoops. So you can see this steadily upward going trend. You can also see these little ripples. Every one of these little ripples is an annual cycle. With vegetative growth in the northern hemisphere in the summer, CO2 concentration goes down and it goes back up in the wintertime as the vegetation decays and releases CO2. We can look back further in time by using ice core data. I'll talk more about that in the next slide. But you can see the Mauna Loa data here, and you can see data constructed from ice cores. And the time scale here is the last 1,000 years. So you can see that there was very little change in that 1,000-year period in carbon dioxide concentrations. It was right around 280 part per million. That means in a million molecules of air, 280 were CO2. But you can see that starting, somewhere around 1850, you can see the concentration start to go up. And if I asked you all what was going on in 1850 that caused this, you would all go, oh, it was the start of the Industrial Revolution. And people started burning coal. Okay, now we're going to look way back in time. The time scale down here goes back to 800,000 years. All right, and you can see this kind of irregular record, and then you can see this much more regular record over the last 4,000 or 5,000 years. These are ice ages. Each ice age is roughly 1,000 years long. During what we call the interglacials, which is what we are in now between big glacial periods, the CO2 concentration is higher, typically around 280 or 300 part per million. Now, these measurements come from an ice core. This is an ice core that's drilled in Antarctica, and you can see all the little air bubbles that are trapped in it. Because water is a small molecule, the ice crystal form does not allow gases to pass through it. And so these bubbles contain the air that was there at the time when the ice formed. So we can drill these cores, and I say we euphemistically. This is really hard work, so I don't do it. You have to go to Antarctica, and you have to have this big machine, and you have to drill this thing out, and then you have to keep it frozen while you take it home, and then you slice it into pieces, and you evaporate it very carefully and collect the air that's in there and measure the concentration. This is actually done very accurately. We know this very accurately. All right, so here's where we were from roughly 8,000 BC to 1850. It's been roughly constant at this 280 part per million interglacial. You can see that on this sort of time scale, we have jumped to the 400 part per million we're at today. Where do we expect to be by 2100? Well, if we went into sort of a utopian time frame and stopped using fossil fuels and emitting CO2 as fast as we could, we might peak out here at about 540 part per million at the end of the century. That would be double what we originally had. If we continue on the path of the Paris Accord, we'll come to that later, it would be about 3 times, 670. If we continue at the rate we were going early in this century, we would be at 1,000 part per million or pushing it. What effect does this have on our climate? Well, this is a reconstruction of global temperature over the last 150 years, roughly. And you can see it kind of wandering around. You can see that the line is thick here, representing the fact that we don't know the numbers as well as we do now because we have a lot more measurements and we have satellites. And you can see that for the last 50, 60, 70 years, we've been on a pretty steady climb. If we go back further using what we call proxy data, things like rings of trees and the like, this is what it looks like over from about year 300 to current. And you can see this part of the curve does not look anything like this part of the curve. We are doing something different, and we know what we're doing, and we understand the physics of it very well. We have other measurements. These are what I'd like to put up here because I think these are a real triumph of science. They're measured from satellites Grace 1 and Grace 2, which are NASA satellites. And these satellites actually measure the Earth's gravitational field to extremely high accuracy. And from that, you can deduce a change in ice mass. And this is the change in ice mass for Antarctica and the change in ice mass for Greenland, going back to the early 2000s when Grace started. It's clear evidence that the ice caps are melting. This is a different way of looking at it. Climatologists typically think in 30-year averages. We don't think 10 years is enough. We like a couple, 2-3 decades. So these are 3 decades. So there's a decade between 1991 and 2020 and a decade between 1981 and 2010. And these are the difference between these two 30-year averages. So these two 30-year averages have in everywhere in the United States is basically, with a little exclusion here, everywhere is warmer than it was. I draw your attention to this because I think this is even more interesting than this guy. This is the precipitation change. And you can see that this side of the continent has dried out and this side has gotten wetter. So when we talk about climate change, it's not just a warming of the globe, it's a shifting of climate patterns, and it's a change in the hydrologic cycle that responds to this warming climate. So we're not just going to experience a slightly warmer place, we're going to experience a place that has some places significantly warmer than they used to be, and has some places significantly wetter and drier than they used to be. I don't want to talk about this too much other than to point out that we have these large, complicated global climate models, and we use them to not only match what has happened in the past, but also to project what's happening in the future. And these models are very good. These projections, however, are only as good as the information that we can put into them about how society is going to use energy and use fossil fuels. So these different curves show our anticipated temperature change. This one here is drastic cuts in fossil fuel use, and I can tell you right now, this isn't happening. There's nobody going to do this, so we can forget this. This couple in here represent a sort of aggressive transition to green energy, trying to phase out fossil fuel and doing it in a reasonably fast manner. This one here is business kind of poking along as we were. Right now, we're somewhere between these two. If we go back over here, if we continued on where we were at year 2000 at the same rate, we would be passing something like 4 degrees centigrade warming, 8 degrees Fahrenheit. By the end of the century, right now, we're more in line for something like 2 degrees, but only if we make this aggressive transition. What are the outcomes of this? Well, this is a different way of looking at it. These are projected impacts of climate change. And up here, you have the increasing temperature going from 0 up to 5. These are different categories. The yellow colors are warnings. The red colors are, you got a major problem. So for instance, when we talk about food and agricultural systems, a little bit of warming may actually cause an increase in yields in high latitudes. But as the warming goes up, we have a real problem in the tropics. The tropical crops can no longer grow because it's too hot. And also because the water availability changes, and we end up have failing crop yields and famine. Water, glaciers are disappearing. We have decreases in water availability. This is a complicated thing to perhaps explain. One of the ways that we often talk about it as climatologists is that as the climate gets hotter, wet places get wetter and dry places get drier. The hydrologic cycle accelerates, and places that already have intense rain tend to get more, and places that don't have rain get less. And that leads to a problem with water availability. Ecosystems, we're seeing lots of extinction, and we would increase that rate of extinction will increase. Extreme weather events. We are experiencing lots of extreme weather events all over the world. And this again is a complicated subject. A lot of people want to argue that you can't tie these to climate change. I don't know if I have any baseball fans in the group, but I always like to compare it to Barry Bonds and his steroid home runs. When he hit 70 home runs in a season, I can't tell you how many of them were due to being, which ones were due to being on steroids, but I can guarantee he wouldn't have hit 70 home runs if he wasn't on steroids. So I can't tell you exactly what the magnitude changes in storms are because of climate warming, but I can tell you that you wouldn't have the ones you have if you didn't have a warmer climate. Okay, so let's switch topics a little bit now and talk about reducing emission. 2015, we signed the Paris Climate Agreement. Due to a particular administration, we bailed on this for 4 years, but we're back in the treaty for now. This is historical U.S. carbon emissions going from 1990 to 2020. And you'll notice that they were on a trend. And if I went back further, you would see they really were on a trend. And you can say, well, look, we're doing good. We've flattened out. And I can tell you, yeah, we did, but this wasn't us in instituting any policy. This is because we figured out how to do fracking. And so fracking made natural gas cheaper. So we switched to using natural gas as a fuel instead of carbon, and we get more energy per amount of CO2 generated from natural gas. So this is really due to also we offshored some heavy industry that used a lot of energy. So this is more a shift in what was going on in the US than it was by any design policy. Here you can see the pandemic, and this is what the suggestion is for current policies going forward. Now, the two lines to really take note of is if we're going to meet the Paris Accord of 2 degrees, we need to be doing something like this. All right, we need to be reducing these emissions drastically by 2050. All right, this is a half. All right, if we want to keep it at 1.5, which is much more desirable, then we have to be down to something like 10% of the emissions we had by 2050, 30 years from now. This fair share, I'm not going to talk about too much, except to point out that the United States owes more to the rest of the world than just doing its share by numbers. The reason we have all of this CO2 in the atmosphere is because we are one of the countries that put it there. And so doing our fair share requires us to be most aggressive about getting rid of CO2 emissions and helping other countries to do so as well. Okay, so now what are we going to do? Well, one thing we could just do is give up on the 2-degree limit. We could just say, well, we're not going to get there and we're just going to have to live with it. We call that adaptation. We could make really drastic cuts to emissions in the next 10, 15, 20 years, and we're going to call that mitigation. And finally, we could maybe find a way to cool the earth in the near term, and that's going to be called climate engineering, and I'll talk about that more obviously in a few minutes. So the way to think about this is here's the climate system. Here is the input humans action causing climate change. Here's the output climate impacts on humans and the rest of flora and fauna. So mitigation is attacking this side. This is doing what we can to stop the human actions that are causing climate change. Adaptation is saying you're just going to live with it and you're going to deal with stuff as it happens over on this side. And climate engineering is saying, okay, well, maybe there's something we can do to the climate system. One way to think about mitigation before I get to the climate system, a way I particularly like is something called the stabilization wedges. You can find more about it at the Carbon Mitigation Initiative at Princeton University. And basically, these couple of engineers thought about this quite a while back, and they said, look, what we need to do is get off the ramp we're on, and we need to reduce ourselves to no emissions, and then we need sorry, I should have clicked that up yet. And then we need to decrease emissions. And so their goal was to take this ramp we're on and cut it down to same emissions every year, no emissions growth, and then tackle the problem of how to get it down to zero emission. Well, as I just showed you, we've actually, because of things that have gone on, we're not too far right now in the US, certainly not globally, but in the US, we're not too far off of this path. So we really want to start looking at this. And they said the way you have to look at this is you don't do this all with one thing. There's a whole bunch of little wedges in here that each take a part of the burden. Now, one thing I want to know, so there's two things I want to tell you. One is there's no silver bullet here. There's no one wedge that's going to do everything. I like to compare it to silver buckshot. You got to do them all. The other thing is we don't have 50 years. We need to move much faster than that if we're going to stick to a reasonable climate change of 2 degrees. And even that may be unreasonable, but better than 4. So what are these wedges? Well, I want you to know I had this slide already looking like this before I ever came to talk to this group. All right, so this little guy down here I didn't add because of you. This is one of the wedges that needs to be considered in this whole issue. There's wedges that can be supplied by energy efficiency and conservation. And this actually is a much bigger deal than most people give it credit for. There's a lot that we could do. I mean, electrical vehicles are becoming much more common, and they actually are part of conservation because it costs you less carbon to generate the electricity for your electric vehicle than to burn gas. Fossil fuel-based strategies, like I said, we're already doing this, replacing coal with natural gas. This is being driven by price. Unfortunately, we can't convince certain people who represent certain states like West Virginia that coal is done and we need to get out from coal as fast as possible. Carbon capture and storage is something we'll talk about in a minute. And then there's the whole issue of renewables and biostorage, solar, wind, biofuel, and the like. Okay, so what about adaptation? Why don't we just bite the bullet? Well, there are going to be huge costs associated with infrastructure to preserve coastal cities. I don't know if you've seen any of this. It just showed up a little, maybe 2 weeks ago. There was a discussion in Miami about building huge seawalls to keep the water out of Miami because they're already flooding. The sea level's gone up enough and Miami sunk enough that they're already flooding at high tides. And the issue was kind of funny because in one way, sad in another, but kind of funny because people were saying, you can't do that because it will destroy our city. We won't just be able to walk out, to the beach. There'll be this big wall in the way that we have to go up and over. And yeah, well, that's going to be the issue. There are going to be climate refugees. There are going to be tropical islands which are no longer inhabitable. They're already becoming uninhabitable because of sea level rise, and there will only be more. There will be countries like Bangladesh where 70% of the country will be underwater by the end of the century. Where are those people going to go? Are we going to raise our hand and say we're going to take climate refugees and resettle them in the United States? Somebody's got to do it. I mentioned this earlier, the tropical agriculture failures. How do we feed these people? So adaptation has its own issues. All right, so what about geoengineering? Well, there are 2 types of climate engineering. One is carbon dioxide removal. And this is the idea of capturing CO2 at the point of fossil fuel generation or removing it from the atmosphere and storing it somewhere else. This is a really important topic. It's a subject for a different seminar. The only thing I want to say about it right now is that we have some activity, we being the sort of scientific and engineering community, have some activity going on in these areas, but we have nothing at the moment that scales to the capacity that we need in order to have an impact on the CO2 problem at the moment. The second kind is solar climate engineering, and that's what I want to spend the rest of my time talking to you about. So the idea here, remember way back, I showed you the planet with solar radiation coming in and infrared radiation going out, and the infrared radiation from the atmosphere warming the surface. So if I reduce the amount of solar radiation going into the system, I could in fact cool the planet down, right? Simple energy in, energy out. If I put less energy in, then I am not going to have and I keep the same going out, I'm not going to have the same temperature. So how would we do that? Well, we can make aerosols, we can make cloud seeding, we can make space mirrors. So let's talk about this a little bit. Before we do that, let's think about what we would do with climate engineering. So think about this as some climate impact. It's easiest to think about this as temperature. Business as usual, whatever we're doing is driving this up. We cut emissions aggressively, and so we have less of a climate impact as time is going along this axis. And maybe we figure out how to do this CO2 removal in 40, 50 years, and we actually start bringing CO2 down, and we start bringing the climate impact down back to where we were when we started with all this mess. Well, what's the role of climate engineering? Climate engineering is a way perhaps for us to temporarily flatten off this heating. It's a way for us to reduce the heating for a while. And I want to emphasize that for a while. You cannot do solar climate engineering indefinitely. You simply can't put enough stuff in the atmosphere to counter 1,000 parts per million of CO2. It's not going to happen. We also have problems that as we add CO2 to the atmosphere, we are shifting the acidity of the ocean in a way that is being highly detrimental to ocean life. So it's not good enough just to say, well, we don't have it in the atmosphere, we can't have it in the ocean either. So we need to figure out how to get CO2 emissions down to zero, and we need to figure out how to start removing it from the atmosphere. And so this whole business of climate engineering is a temporary solution. And you're going to say, well, what's temporary? Temporary is not 10 years, it's probably something like 30 to 50 years. Okay. So the simplest thing to do conceptually to do climate engineering is just move the Earth. All right. If we simply move the Earth a little bit further away from the sun, I figured it out one day. I figured we need to move the Earth about 220,000 kilometers further away from the sun to compensate for a doubling of CO2, 500 parts per million. That's not very far. It's only about 200 kilometers a year. You know, we should be able to do that. Archimedes said we only need a lever. The problem is we don't have a place to stand to use the lever. So this is an interesting calculation, but obviously not going to happen. There's a bunch of talk over time about sunshade and mirrors. You could put sunshades up, and this is a fun thing to talk about, but there's two things that are a problem. One is it's really cost effective. The other thing is once you get them up there, if you don't like them, you have to get them down again. And that would be a game sort of like the ultimate, you remember the old asteroids on your computer a long time ago where you tried to shoot things down? It would be a little bit like that, asteroids in space trying to shoot these guys down. The more realistic things that we've talked about are this one, which is volcanic eruption. We know that volcanic eruptions cool the climate. Mount Pinatubo erupted in the Philippines June 15, 1991, put a whole lot of stuff in the atmosphere, particularly a lot of sulfuric acid particles in the stratosphere. This is a picture taken from the space shuttle, and you can actually see in the limb of the planet, looking through the atmosphere to the limb edge of the planet, you can see these layers of aerosol. And we know that this actually reduced the temperature of the globe for a couple of years. The lifetime of these aerosols has an e-folding time of about 2 years. So they're pretty much gone in about 4 years. All right, so we know that we can put things up there that would cool the planet. There's a group at Harvard which has spent a lot of time thinking about this, has actually spent some time and money to develop an experimental platform which would put particles in space and would have instruments on this, and they would lift it up with the balloon and drop it back down to measure what would happen. This is the kind of thing you have to do to test out how long these particles will live, what their concentrations are, what their size are, what do they do to solar radiation. They originally proposed to do this experiment in Texas in 2019. It was delayed for technical reasons. They proposed to move this to Lapland in Sweden due to COVID restrictions. It was scheduled for summer of 2021. It was opposed by a variety of environmental groups, particularly the indigenous people of Lapland, and permission was revoked by the Swedish government. Now, I want to point out that there is nothing in this experiment that is harmful to the environment, really. You're shooting a handful of particles into the atmosphere. There's no comparison to what a volcano does, and volcanoes are doing all the time. There's always stratospheric aerosol. But just the idea that humans were going to go in the stratosphere and mess with it was enough to freak out Sweden. So the latest news is Sky Luke Eisenman, a really arrogant American, assumes he can do whatever he wants in Mexico. So he takes this weather balloon, which he bought on Amazon, fills it with some small amount of sulfur dioxide by burning sulfur, launches it on April 11, and says, I've done the first stratospheric aerosol experiment. Now, nobody knows where this balloon went. Nobody knows how much was in it, and nobody knows whether it ever got to the stratosphere or not. Okay. What happens? Mexican government responds 2 weeks ago, experimentation with solar geoengineering will not be allowed in Mexico. So we're research-wise in a world of trouble with climate engineering because of people like this and because groups don't understand what we want to do. The second thing that we've talked about is something called marine cloud brightening. And this is something that our group here at the University of Washington has taken the lead on. So I'm quite familiar with it. This is a cartoon which was in the, the British magazine. I'll think of it in a minute. And I love it because they're suggesting we're salting the clouds. There's somebody, politician, presumably turning on and off the salt shaker to change the climate. And this is sort of me down here, or my group, tinkering around with the mechanics of this. So it's sort of a tongue-in-cheek look at it, but I like it. All right, natural analog. These things in this is California. These things in here are called ship tracks. These tracks were identified probably around 1990 from satellite photographs, and at first were somewhat mysterious, and then gradually figured out, a bunch of people looking at them, that these are ships, big container ships, tanker and the like, that are going along underneath the cloud. They're underneath these stratus clouds. They're emitting particles. Those particles are seeding these clouds and making them thicker. And the interesting thing is that these cloud tracks can last a long time. This isn't just a snap. I mean, these are going on for a day. Basically, without spending a lot of time on the physics, these clouds are starved. Every water droplet in a cloud has to form around a nucleus. Water does not just get around, a bunch of water molecules don't just get together in the atmosphere and say, oh, let's hang out together and be a drop. They have to condense on something. And that something is always a little particle. So the number of cloud drops you can get is limited by the number of particles in the atmosphere. Over land, we never seem to have a shortage of particles. They come from all sorts of places, blowing dirt, tree, pollen, whatever. But over the ocean, it's very clean. So these clouds don't have as many drops as they could because there aren't enough nuclei. So if I add salt crystals, which are very good nuclei, to the clouds, I can make more cloud. Clouds are shiny. Ocean water is very absorbing. So this changes the reflectivity of the planet. Okay, so a conceptual view of how we might do this is we would have self-propelled ships wandering around, spewing salt water into the atmosphere, producing all these little particles. We would steam them around underneath marine clouds that are susceptible, and we would have thicker clouds and a cooler planet. One of the things that's interesting is when you start doing things in the stratosphere, you're pretty much forced into a sort of hemispheric response because the circulation of the stratosphere will spread the stratospheric particulates. And the lifetime, as I said, is a couple of years. So you're just going to have to wait around, and it's going to be largely cooling an entire hemisphere, maybe the globe. But marine cloud brightening can be applied regionally whenever there's a particularly good cloud cover, so it can provide local cooling. So we think it can affect regional climate systems. Maybe we could selectively cool the ocean over coral reefs to prevent the water from getting so warm. Maybe we could alter circulation along the coastal California area to produce more onshore flow and moisture for coastal systems that are struggling, like the redwoods. We could produce global cooling by summing many regional coolings, but we're uncertain about how that cooling propagates around the world. So we need a lot more research. So an experimental marine cloud brightening project would look something like this. You develop a sprayer that sprays salt into the air. You do a spray system development and test it. You do coastal and ocean tests with a single ship, and then you do a limited area experiment with multi-ships over an area like 100 to 500 kilometers by 100 to 500 kilometers to see how it works. If you want to know more about that, here's an article that I've written with my colleague Rob Wood in October of 2012, which is actually a long time ago now, a decade. So if we knew all this a decade ago, why haven't we made more progress? Well, basically, until very recently, there was no government funding of any kind for climate engineering research. We could not get anybody to fund even the most basic of research. Recent National Academy report suggested 40 million per year for the next 5 years. It is completely inadequate for the scale of the problem, both of the research that we need to do and certainly the scale of the entire climate change problem. We are simply not investing in this solution. Is it a solution? Well, maybe not, but we won't know if we don't invest in it. I just wanted to give you a picture of this because it's kind of fun for nerdy people. The way that we have developed a little nozzle that puts out about 3 trillion particles per second. We want to put these into a cannon like this, which is similar to the cannon that they used to make snow. It won't be exactly the same as snow making because these are really tiny. And we would blast these off of the deck of a ship. We could also put something like this on the back of an airplane and blast it out the back of an airplane. But in the long term, you want to do it from a ship because it's a lot cheaper. And it doesn't require a lot of fossil fuel to run the airplane. Can we do this? I don't know. We think so. We're going to do the experiments. If we went ahead with a kind of full bore program, and this is sort of similar to the same thing for stratospheric aerosol injections, what do you need to do? Well, I want to point out here that there's a field program that we want to do. We need to do things in the atmosphere. We actually need to go out and try these things. I sometimes get pushback from this about, well, we shouldn't be doing this. And I go, actually, this is what physicists do. You know, we go out and we do controlled experiments. And I'm an atmospheric physicist. My undergraduate degree and master's degree are in physics before I switched over to atmospheric science. So I think of this like a physics experiment. Okay, we need to do high resolution modeling, and this LES stands for large eddy simulations. That means they're done at very high resolution, and we're actually trying to model the very formation of these clouds and the circulations that lead the clouds. We need to have community engagement. One of the reasons I put up the thing about Mexico is it is critical, if we're going to do this kind of research, to engage in conversations with the local stakeholders, to tell them what we're doing, to answer their questions, to point out to them that we're not doing anything that's not already being done. The amount of stuff we would put in the atmosphere for our one ship experiment is less than what comes out of a tanker every day. Look at the ship tracks. All right, so we're not doing anything unusual here. We're doing something with a different purpose. And finally, we would need to do lots of global modeling to understand the total impacts. So all of this has to be done. It's not just, oh, let's run out and do a project. I mean, this is the kind of thing that got the guy in Mexico. I mean, he didn't do any of this, right? He just released a balloon and said, there, I've done it. Good me. All right, so now let me switch gears. Part of stakeholder engagement is not just about, are we doing harm? It's about a much broader ethically troubling issue. And I want to point out that climate engineering is an incredibly complicated ethical issue. And I'm going to spend a little bit more time talking about that. But I want to read this quote, and I see my time is fleeing quickly. This is from my friend Steve Gardner, who is a professor of philosophy here at the University of Washington. He and I have co-taught a class twice together on climate and ethics of science and ethics of climate engineering. He's also written this book. The point Steve is making here in this article is that the decision to pursue solar climate engineering is being made under compromised circumstances. It is because we have failed and continue to fail to do what we should have done, ethically speaking, that is, to seriously decrease emissions. It's only for that reason that we are considering climate engineering, geoengineering at all. And he's absolutely right. If emissions were decreasing, you wouldn't have people like me thinking about how can we keep the planet cool until we actually do the right thing. Hence, in the ethics of geoengineering, it is as if we were asking a paradoxical question. What should we do, ethically speaking, given that we are not done and that we have not done and will continue not to do what we should be doing? All right. So all of us are participating in a failure, an ethical failure to deal with a problem that we know we have. So I want to think about this problem now for a few minutes in terms of science. Can we do it? Ethics, should we do it? And governance, how do we do it? I'm going to have to go through these way faster than I wanted to. Moral hazard is the technical fix to a behavioral problem. This is the idea that your waterfront property gets wiped out by a storm and you're expecting government to rebuild it for you. All right. You're not addressing the real problem, which is you shouldn't be building on the shore in the face of a hurricane. That's a moral hazard. The moral hazard here is we're trying to come up with a technological fix to something we should be doing in the first place, which is emitting CO2. This whole idea of hubris is one I could talk about for quite a while because I really think it's appropriate. Should we be engineering climate? Is this something that we as a human race should be doing? Are we playing God? Are we exceeding our place? Are we exceeding our abilities? I'm often run into people who want to talk about saying, well, you shouldn't do climate engineering because you don't want to do any harm. And I go, no, wrong. We are already doing harm. We are already harming the system by adding CO2. So the question is, are we doing less harm? Is it the lesser of two evils to do climate engineering compared to just let climate change go on unchecked? There's a complicated question here of what we call evidentiary threshold. It's basically, when have we done enough experiments to proceed if we're going to do this? Who decides that we know enough to go ahead? Is there a difference between long-term testing and deployment? I like this quote from Samuel Johnson, who says, power is not sufficient evidence of truth. The point here is, just because you can do it doesn't mean that you got the right to do it. And you need to be able to answer these questions. There's whole issues of justice. Who's responsible for the mess we're in? Who determines what the climate should be? How far do we want to turn the dial back if we could? If we could turn the dial back to where we were in 1850, I'm sure there'd be a bunch of Scandinavian countries, parts of Canada, be going, no. We're happy with a little bit of warming. That degree or so of warming we got has been real helpful. Who pays? The countries in red here have largely contributed nothing to the CO2 problem. It's almost all the countries in blue. And then this one is a particularly worrying and difficult question to answer. What's our responsibility to the past and the future? Again, I could talk a lot longer about this. When I say our responsibility to the past, we all have parents and grandparents who left us a legacy. What are we doing to that legacy? And do we have the right to do anything that we feel like to that legacy? What about the future? What am I leaving to my children and grandchildren? I thought of popping up pictures of all my cute grandchildren, who are much cuter than anybody else's grandchildren. But I thought I wouldn't do that. Their parents might not appreciate that. But I think a lot. My wife and I think a lot about this. What are we leaving to our grandchildren? Okay, I'm going to hop over this and go straight to this. The bottom line, for a science point of view, we have a very good grasp of how our current climate works. Climate's changed over the past 100 to 150 years and is changing rapidly compared to changes in geologic time. Our projections are dependent on emission scenario, how energy gets used over the next year. But we understand the direction, we understand the global magnitude, we understand less well precise magnitude and regional variability. And it's pretty scary in terms of its potential impacts. The science is sound. The science community is hugely in agreement. What about the ethics? Our choices are limited. We can change our behavior. We can adapt to the consequences. We can try to engineer our way out temporarily. Climate change involves ethical issues, not just scientific issues. You cannot divorce them. I'm very fond of the statement that a budget is a moral document. And you go, what? It's just how I spend my money. And I go, exactly. You are making moral choices when you decide how you're spending your money. We are making ethical choices in our government in Washington every time we put out a budget about how much we think should be spent on Social Security, on welfare, on defense spending, on mothers and children programs, on immigrants. All of that are moral questions. A climate change plan has exactly the same. Climate change will be felt most dramatically by the younger generation. Our children and grandchildren are going to experience the serious impacts of climate change. What can you do? Well, you can change your personal behavior, get your family and friends to do the same. And I think it's important for us to emphasize this, but it's not enough. We need to influence our politics. We need to vote. We need to contact legislators. We need to use institutional powers as groups, whatever they might be, your group, university groups, church groups, whatever. I want to point out that you actually have an advantage in the Tri-Cities. I did live in the Tri-Cities for a while. Your representative is actually a Republican. You could actually get a hold of him and tell him that he needs to do something about the climate change problem. My representative is one of the most left-wing representatives in all of Congress, so there's not much point in me calling up Pramila and saying you ought to do more. So I encourage you who live in a Republican district to emphasize to your Republican legislators that this is not a political issue. This is a human issue. Earth, it's the only planet we got. Thanks for listening. And I'm happy to answer questions.
I'm going to go ahead.
Oh, go ahead.
Oh yeah. So let me make sure that I get this second camera off our stream. There we go. Okay. All right. Everyone's done sharing slides, and everyone in the audience, you may raise your hand. If none of us recognize you, you won't be coming on stream. And because you mentioned the representative we share, Tom, I'd like to ask you, please do ask Pramila if she could support nuclear energy. I think that you would have a great impact. You made a great point that you supported nuclear before you came to talk to us. So I'm happy to hear that from you.
That is a fair point, and I will take that under advisement. That I need to practice what I preach. It's not just other climate solutions that should be considered.
All right. So I see Nathaniel.
Only if you contact Dan Newhouse, okay?
Okay. Well, I'm in Pramila's. I'm in hers.
Oh, okay. Sorry.
Everyone who's in Newhouse's, please. Let's be clear. We're now a nonprofit, so we can say you have the option. And my appeal to Thomas was a personal one. So I'm going to go ahead and allow.
I also, before anybody gets upset, I want to point out I don't think Dan Newhouse is a bad guy. Actually, one of his cousins is one of my longest and dearest friends. So he's not a bad guy. I just wish that he would recognize this problem for what it is and not see it as some sort of red-blue problem.
Okay. And Lila, if you don't mind, you can take over selecting people to speak. I've got Skip and then Jim.
Sure. Let's see. Skip, you had a whole bunch of questions here, and do you want to go ahead and ask them, or should I read them off? Or
I can just ask the most pressing one since we're running out of time.
Actually,
my concern is that,
so regarding time, we can go as long as you want. I mean, we won't go back past 2 hours, but as long as everybody's willing.
Okay, very good. But those that have to drop off, I think the most pressing question I have is if you start, it's the bounce back effect from any geoengineering. If you start doing ship tracks or other atmospheric or any type of geoengineering, you can't really know completely all the impacts until you get into large scale. And if we don't reduce the CO2 correspondingly, the potential for a bounce back impact, if you stop on the impact on the globe, could be huge. So I understand that we may jump into that, but I'm very concerned about the effects of pushing ourselves to a lower temperature and then all of a sudden bouncing back to a very high temperature when we have to stop for whatever reason, whether it's political, terrorist, unintended impacts, or whatever.
Okay. The issue you're raising is an excellent issue for us to talk about. I want to try and separate a couple things which maybe are a little muddled in there. First of all, let's just think about stabilizing temperature. If we could just stabilize temperature where we are right now, we're not talking about making the planet cold. All right? We're talking about just trying not to let it get warmer. We're not talking about doing enough climate engineering to actually cool the place down. Right now, we'd just be delighted if we could figure out how to stop it from getting any warmer. All right. So the question then is, if I can slow it down from getting warmer, and I'm doing climate engineering, I'm seeding clouds and I'm making cloud brighter, and then one day I quit. All right. What happens? Well, what happens, at least in our modeling effort, is when we try that, is the system very rapidly climbs back to where it would have been if we'd never done any climate engineering at all. So The question then is that worse or not than if we had never done the warming? One argument is, well, at least you bought time. You kept it cooler for a while. The other is, yeah, but you didn't allow the systems to equilibrate slowly instead of rapidly. Well, that's true, but most of our systems can't equilibrate in the time scale of 30 years anyway. We're doing steady damage to them as we go along. I think it's definitely worth us thinking about, how does this rebound problem work? What actually happens? And the way we can do that right now is with models, but again, somebody's got to underwrite those efforts. One more thing about this whole issue with marine cloud brightening compared to stratospheric aerosol is I can modify a piece of the atmosphere, a local piece of the atmosphere. So I can ask what happens locally without having to influence the whole globe. And I think that's a huge advantage. I hope that was a good enough answer to a really complex issue. Next.
All right. Okay. Let's ask James Conca to unmute.
Oh, no, he's not allowed to talk.
Is it, I mean, I love Skip's question and all that, but in the ethics, but we're going to burn. Okay. You have to keep that in the back of your mind. We're going to burn. And so all of these like lazy, chairs, whatever, we don't have the luxury of this, and things are moving fast and we're not doing what we're supposed to do. But could you do two birds with one stone? Could you inject into the stratosphere, basically crushed limestone, which as it falls out would actually address global ocean acidification somewhat?
Not likely. First of all, the amount you got to think about scale here.
Yeah.
The amount of stuff you need in the ocean to counteract the CO2 in the ocean is a lot more than the crushed limestone you're going to put in the stratosphere.
Right. Okay.
And the stuff that comes out of the stratosphere, interestingly enough, does not fall into the ocean. Most of it is removed over the Arctic and Antarctic, or in what we call deep tropopause folds during the wintertime. I don't want to bore people with stories. My kids always tell me I'm too full of them, but there's a wonderful story of, I mean, it's sort of sad, but in the 50s, it was identified that there was strontium in milk being delivered to children in New York City. And people went nuts. Where is this stuff coming from? Well, it turns out that it was coming from the stratosphere. It was put into the stratosphere by tests of nuclear weapons. The fallout ended up on the grass in New York, eaten by the cows, passed on through their milk to kids in New York City. So we know where the fallout goes. We want to be careful about what we consider fallout. So I don't think you can kill two birds with one stone that way, Jim.
Okay, good. But certainly limestone is fairly benign, as opposed to
it is. And one of the issues with so the original thought for stratospheric aerosol injection was to put up sulfuric acid, right, sulfur dioxide, which is what volcanoes do. One of the downsides of that is that you end up affecting the ozone layer. So people have been on a hunt. The guys at Harvard have been on a hunt to try and find something else that they could put up there that wouldn't have the effect. And in fact, one of the candidates is calcium carbonate. But I would point out to you, Jim, that the thing they found that works the best from a theoretical point is ground up diamond dust. It's
the other issue is we need billions of tons of this stuff, and we have billions.
Right.
Of tons. Right.
Right. Exactly. I just wanted to point out theory's great, but practice doesn't always work.
Yep. Thank you for doing this.
You're welcome.
Okay, it looks like Sidesh, if I'm saying that correctly, you have a question. You can unmute.
Thank you. First of all, Thomas, thank you for the great presentation. It's very educational. Thank you for that. My question is regarding the solar climate engineering, like putting up mirrors in space or
Yep.
shade and sort of reducing the amount of solar energy that comes into the atmosphere. So isn't the amount of solar energy that comes into the atmosphere a very much part of all the life operations here on Earth? And do we see any kind of harmful effects of reducing the amount of sun that we are essentially getting?
Yeah, that's an excellent question. And I mean that sincerely. And it's one that we have certainly thought about. We're not talking about an enormous reduction in solar radiation. So one of the questions that you have to ask is, what's the efficiency of, for instance, plants? How much, if you reduce solar radiation a few percent, is that going to affect plant growth? Is that the real limiter? And the answer is no. Almost always the limiter in plant growth is not photons, it is nutrients. I've talked to my friends in the ocean community, and I actually, at one point, began a project which unfortunately failed again for lack of funding, to try and do some simulations of what reduced solar radiation does in the ocean mix layer. Does it have an effect on the productivity of the ocean mix layer? And the interesting answer I found was, at sort of a hand wavy scale, was that if you look at an ocean column, the little critters in the ocean column actually move up and down depending on how much solar radiation there is. In other words, they're already trying to protect themselves from too much. They go a little deeper down in the water column. So most of what I've seen, and this is not exhaustive, and it's something that I think we would need to do a lot more work on, is that the amount of solar radiation is not the limiting quantity for most of life. So reducing it 1% or 2% probably isn't the biggest issue.
Got it. Thank you for clarifying.
Okay, looks like Don Jordheim, if I'm saying that right, is got your hand up. Go ahead.
Yeah, thank you. So Dr. Ackerman, my question has to do with methane, actually. In the early part of your presentation, where you covered the basics of how carbon emissions are driving global climate change, you didn't happen to mention anything about methane. You did make a point about how, to some extent, we've at least reduced coal usage in power generation, and it's been largely replaced by combustion turbines fueled by natural gas. And I'm sure you're aware there's an awful lot of methane release associated with all that. I have read in more than one place claims that in the end, the natural gas turbines are in the end not really better than coal burning power plants regarding global climate change because of the methane releases. Can you weigh in with your 2 cents on that?
Okay, you're going to get 2 cents worth. The methane problem is one that I've tried to stay out of. Mostly I'm an atmospheric physicist, and so I don't want to do chemistry problems if I can help it. And methane is notorious because we don't know where all the sources of methane are. All right. If you look at a single methane molecule, adding a single methane molecule to the atmosphere is a bigger greenhouse effect than adding a single molecule of CO2. But the lifetime of methane molecules in the atmosphere is only about 10 years, whereas I said the lifetime of CO2 is hundreds of years. So the cumulative effect of adding CO2 is a lot more. Now, on the short term, if you have a process that generates a lot of methane, you can say, well, I've saved some CO2, but I generated methane. I didn't win anything, but you will over time because the CO2 has a much longer life scale. I am not familiar enough with turbines to know how much methane generation there is from natural gas. I do know there's an awful lot of methane that's released in the process of collecting natural gas. And that's why you see all of these flaming little torches in natural gas fields where people are just igniting the methane and throwing it away. So one of the things we can think about is how do we make a better use of this resource? The other thing which I think is interesting, And some of you may know in the vicinity of where you are, if you're in the Tri-Cities, in the vicinity where you are some major league dairy. And those dairies have lots of dairy cows, and those dairy cows are producing lots of methane. And there are various things going on where people are trying to figure out how to do a better job of collecting that methane and actually using it. And I think those are commendable. Again, we can talk about whether one should be a vegetarian or not, but I'm not going to sit here tonight and tell you all need to give up eating beef. I had tuna for supper tonight, so I'm good there. I didn't have any beef. But I think it's useful for us to think about how do we do a better job with agriculture in terms of cleaning up greenhouse gases. And there are certainly things we can do. I hope that was 2 cents worth, Dan.
Thanks. That sounded good. Let's see. Skip, I'll come back to you in a sec. I think your hand's still up. You might make another point. Somebody has made a point a couple of times in the chat about the problem with ships is that they burn bunker fuel, which is really, really filthy. So you want to speak to that just a little bit?
Yeah, well, that certainly is a problem. And there are efforts underway to make ships clean up their bunker fuel. Will that happen? I know that's above my pay grade for sure. When we talk about ships for doing the marine cloud brightening, I showed you that sort of futuristic little guy that would be running around as a robot ship, basically wind powered. We don't need these things to go anywhere particular. We just need them to sort of sail around underneath clouds on scales of 100 to a few hundred kilometers. So we could actually put ships out there that don't require any fossil fuel, and that would be certainly an attraction. You don't want to be burning fossil fuel to prevent the, generating more CO2. But the long-term problem of shipping and bunker fuel is one that has a lot of attention right now in a lot of different places.
Great. Skip, go ahead. You have probably another question.
Just a comment on
yes,
that. I think Seaborg in Denmark is working with, I can't remember who it is, but they're looking at doing SMRs and cargo ships. So that's pretty exciting.
Sorry, doing what in a cargo ship?
Small modular reactors.
Interesting.
Yeah, very exciting.
Yeah, very doable from my experience in being in the Navy on nuclear subs. Dr. Ackerman, I do want to thank you for your previous answer and for coming here and doing this. This is a fantastic presentation. I feel very privileged to be able to listen to your talk.
That's very kind.
So thank you on that. There are 2 quick questions. One, have you ever heard of Vesta.Earth and their proposed use of olivine on coastal areas where they're saying that 0.1 to 0.25% of the coastline should be able to reduce about a gigaton of CO2 per year. That's part one. And then part two, has anybody modeled how the governments and world populace are going to react when we experience the first tipping point, such as the collapse of the Thwaites Glacier? Because I think people are going to stop equivocating. They're going to start saying, why haven't you been doing this?
I'm certainly glad that people ask me simple questions with simple answers. Nothing better. So the answer to your first question is I've heard of it. I don't really want to comment on it because I don't know enough to comment on it. Geology is really kind of far removed from my bailiwick, so I'm not going to go there. Second one is the short answer is no. The longer answer is I'm not sure we know how to do that. One of the advantages, I joke with some of my friends, including my daughter, that I'm not a biologist like they are, because I deal with simple systems that have equations that and laws that I understand. As soon as you engage people into the mess, you can no longer model them. All right. So I don't think anybody knows how we will respond. One of our arguments to a calamity, a tipping point, one of my arguments with people about, so why aren't we doing this research, is, something like this is going to happen. And all of a sudden people are going to say, well, you need to cool the planet down. And we're not going to know how to do it. Or we're going to end up with people doing it with completely half-baked ideas because we haven't taken the time to figure out how to do it right. So we needed to start the research program a decade ago. That's what Rob and I were trying to do 10 years ago. And we just can't get any traction. So I don't think I can answer how people are going to respond. I can just tell you that the response right now to the climate change problem, in general, to climate engineering in specifically, is people sticking their head in the sand and trying to pretend that it's not important. And I wish it were otherwise.
I agree. I agree. Yeah, that the one suggestion. I've worked with system dynamics from out of MIT and done modeling with it, and it does a fantastic job of modeling systems undergoing change with human intervention. I don't know if you've ever heard of it, but okay. So one of the problems here is a lot of our understanding of, to some extent, human health and certainly human behavior is based on extrapolation from things we have observed. All right. We try and figure out how things work, and then we extrapolate from there. We're talking about something which we haven't observed yet. We're talking about a giant deviation from the norm. And so I don't really trust models which are essentially heuristic statistical models to handle a really off-the-wall experience. And that may just be my physicist, nose turning up at biology, or it may be legitimate. Very good. Thank you very much for your answers. And again, thank you very much for coming here, Professor Ackerman. Don't get too carried away. Tom will do. No, it's a pleasure. I certainly am always happy to talk to people about the science that we know, the science that we do. I encourage my students to do the same. I think we to some extent live off of a public purse when it comes to research money. And that's a different kind of conversation we could have about public versus non-public funding of research. And part of our obligation then is to explain what we're doing to people. Why are we doing this? We're not, we're not taking money out of the public purse just because we're exploring something that seems cool to us. There's a reason why we're at it.
Let me ask you, I think Sidesh wrote that he had to get off, but he thanked us and enjoyed the conversation. Yeah. He asked an interesting question, which I don't know that we actually covered it, saying that what kind of impact lessening, the amount of sun coming through has on species, human.
Oh, yeah, I answered that. He asked that before he left. Yeah, okay. and I said, I don't think most of the, briefly, most of the species are not using all of the sun that falls upon them. So losing a little bit is not going to be their biggest problem. Their biggest, and in fact, I didn't mention it at the time, but a far bigger problem for most vegetation is water. They're going to be far more upset. Those plants are going to be far more upset by a screwing up water cycle than by changing the sun a little bit. We warn everybody out.
Anybody else?
I think all the questions have been answered in chat. Carl, are there any on the other channels?
Well, we don't have a huge number of people online, but we want to thank everyone for showing up. Looks like everyone's worked it out of their system, and I want to apologize if anyone was a little disturbed by the Zoom bomb. Looks like our security capabilities had changed, but we cleared all of the trolls out, so don't feel at all concerned. I was on the job and got it all cleaned up. I want to say thank you to everyone who checked us out online. I'm going to shut down the stream, and then we can maybe relax our security procedures a little bit and just let everyone have a good chat for maybe 10-15 minutes, as long as Tom wants to stick with us.
Okay, I just was scanning through the chat. I find it difficult to keep track of the chat when I'm talking. But I'm sorry that it doesn't look like Tricia is on anymore. She commented on another book that Steve has just published called Dialogues on Climate Justice. And I was going to tell her that I'm glad she knew about it. And I will also pat myself a little bit on the back for having read and commented on parts of that dialogue. So.
All right. So thank you, everyone. I'm going to send you all on the live streams to the commercial for one of our related organizations, the Eco-Modernist Society of North America. Thank you very much.
I want to speak to you about a new organization called the Eco-Modernist Society of North America. I'm here because we are in the midst of a potentially monumental ecological crisis. It is only through a new environmentalism 2.0 that progress can be made. We believe that our only hope for human advancement and even human survival is through the exponential advance of science in the service of humanity. Eco-modernism is a new environmental paradigm which looks to reverse the fear of nuclear power and scientific progress in general. Ecology-based modernism is the most direct way to define it. Eco-modernism as a philosophy is described in the Eco-Modernist Manifesto. We believe humanity should not be rejecting technological progress, but rather separate our impacts from nature through the responsible use of technology and urbanization. Urbanization is an unstoppable worldwide trend and the best solution to many environmental problems. It offers sustainable development for the human population and is a historic antidote to both deforestation and species extinction as humans move away from using wildlife as their protein source. Vertical, urban, high-rise architecture minimizes the use of land, resources, and energy, enabling walkable cities that facilitates the more efficient use of mass public transit as well. It must be emphasized that our support for technological solutions is definitely not about defending industrial polluters, nor does our defense of technology imply that we just need to sit back and let things take care of themselves. To the contrary, we believe that humanity is at a crossroads that severely threatens our future on this planet. I hope by now you understand the worthiness of our cause. Eco-modernism is really only a philosophy at this time. I want to talk to you about the necessity of turning it into a movement, which will be part of the larger environmentalist movement. For it is only through our presence and participation that there can be any hope of moving environmentalism in the right direction. Our aim is not to divide the environmental movement, but rather to multiply its numbers with the incorporation of many scientific and educational communities that is working to both build chapters of eco-modernist societies and support our growth worldwide.